All right, so we're working on. We'll finish this chapter off, so we'll be done with chapter one. And I don't think we're probably going to be here for the entire hour and a half. So, uh, but there are some calculations and some uh, rounding some values that we have to uh, understand and go over. So, the first part, before we even get into any like significant figures or calculations, is actually just understanding um, our measurements, right? Um, Anytime that we make any measurement, whether it's with a ruler, a scale, a thermometer, measuring cup, graduated cylinder, uh, you know, whatever the vessel is, whatever the instrument is that we're using in order to make a measurement, in order to take a measurement, uh, is that every measurement is going to require one specific thing from you, right? And measurements require a one digit best guess. Not two digits, but at least a one digit best guess. Is that if it, and the one digit best guess, if I had, depending on, let's say we had a ruler, depending on the ruler we had, and I'm measuring centimeters, maybe I'm measuring 1.1 centimeter. But let's say I had like this real expensive, is very accurate ruler. Maybe I'm going to measure it at 1.11 centimeters, 1.111 centimeter. All that depends on the accuracy of the instrument that you're using. So for instance, if we had this ruler here, let's say this is one, two, here is 1 centimeter, 2 centimeter, 3 centimeters, 4 centimeters, and I want to measure this line here. Well, my answer wouldn't be 1 centimeter, right? Um, every measurement that I take requires will require a one digit best guess, right? So this ruler isn't very accurate, but I can tell that my measurement, that this line is greater than 1 centimeter, but less than 2 centimeters. So I would make a guess and say, well, this is 1 point, I don't know, 1.4 centimeters. And that would be an accurate measurement. I could also maybe say, maybe some of you don't see that. Maybe you say, Alex, you're a little off. I think it's 1.5 centimeters. And both of these are correct. Maybe somebody's looking at it and say, Alex, I think you're still off. I think that it's 1.6 centimeters. Well, always remember that it is simply just your best guess. There's never going to be any time where you're going to accurately guess this best guess, right? But every measurement does require it. So, excuse me. Let's say that we went out and we bought a more accurate ruler, right? Instead of going to the 99-cent store, we actually go down uh, to the science store and we buy this very accurate ruler. And now we'll say, let's see, right? Now my ruler's a little more accurate. Excuse me. All right, sorry about that. So now if we take a look at these measurements, well, let's take a look at this. These are no longer accurate because I don't have a best guess. In fact, a couple of these are now wrong. That if I'm looking at this, well, this measurement here, it's definitely not 1.5, definitely not 1.6, but now my measurement here is going to be 1. I'm 100% certain that a 1 exists in this measurement. It's at least 1 centimeter. It's at least 1.4 centimeters, but it's not quite 1.5 centimeters. So again, I require a 1-digit best guess. Maybe it's 1.45 centimeters, where here's my best guess. Maybe it's 1.47 centimeters. Maybe it's 1.43 centimeters, right? And again, this last digit is simply just our best guess. Is that each one of these is an accurate answer, is a good measurement, right? It's a good measurement of what we're seeing. I think the book might show you some as well. So here, right? If we're looking at this measurement here, right? We can't just simply say that it is 21 milliliters because as we can see here, right? Here is, right? Here's 21. Here's 22, and it's right in between there, right? So our measurement here, this is the meniscus that we measure from the bottom of that meniscus there, is that our measurement would be 20. Nope. Our measurement would simply be 21, maybe 21.5, maybe it's 21.4 milliliters, right? But we do have some best guess there, right? So every measurement that we have is going to require that best guess from you. If it's on a stopwatch, it doesn't matter what the instrument is that you're measuring, is that every measurement is going to have some best guess. Uh, even the scales you use, like you guys are on Smart Sparrow in that lab and you guys are playing with the scale, that very last digit is the instrument's best guess. Even though it's digital, that last digit on the scale is the instrument's best guess. All right. So now for all of these measurements that we take. So all these measurements that we take, we're going to now consider what we're going to call significant figures, right? So there's different types of significant figure, how to determine different significant figures and what you're going to need there. So the first rule of thumb for significant figures is that any non-zero number is significant. Right. Any non-zero number. If you want to know what a non-zero number is, it's a number that's not zero, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are all non-zero numbers. All right. So if we give you a value, we say, okay, 287 centimeters, right? Is that all of these, this is non-zero, that is not a zero, that is not a zero, is that this provides me with 3 I'm gonna even make it shorter. What we call sig figs, significant figures, and I'll say this. Let me write it out because there's a few different ways that I do this, so or even say it. So um, three significant figures. We can say significant digits. It means the exact same thing. We can say sig figs, right? Means the exact same thing. And even this S/F, right? Three significant figures, significant digits, sig figs, S/F. They all mean the same thing. Is that here we have a total of three digits that are significant in my measurement, right? The last digit's my best guess, but it is still a significant value. It's a significant figure. If we give you, right, all of these are non-zero numbers. So I would count them all, 1, 2, 3, 4, 5, and I have 5 significant figures. Okay. So that's part of how we determine significant figures. So I don't think that there's a value right now that I could give you that you probably couldn't figure out. We can throw in one more. We can say, here 12, not a zero, not a zero. There's two of them. So this is two significant figures, right? Not difficult to discern and figure out when they're non-zero numbers. It's when we get to it's when we add zeros into the mix. So when we add zeros to the mix, there are four different types of measurements that we could possibly get. Right. Uh, the first type is going to look like this. Right. So here's a value right here. We'll put milliliters. So I have 0.0259. Actually, let me not use milliliters. I'll use liters. That sounds more reasonable. Well, these zeros here, zeros that are in front of your non-zero numbers, right? These are what we call leading zeros. Is the numbers that are in front, right? And leading zeros are never significant, ever. We don't ever count leading zeros when we're determining significant figures. So here I have one, two, three non-zero numbers. I have two leading zeros, but I'm not going to count them because they're never significant. And I have three significant figures. Right? Um, it doesn't really matter how many of them we have. It's irrelevant. If they're in front, they're leading zeros, never significant, and there's never any exception to that rule. Um, so it doesn't really matter how many I have, right? I'll say, kilogram here. That this is going to be simply be, here's my non-zero number. These happen to be leading zeros. I'll do the same thing for here, right? Leading zeros. And I have one significant figure. Um, I don't even need the decimal isn't even required. I could simply write this, right? Decimal's not even required, but these zeros are out front, right? Again, here we have, oops, these are leading zeros. The only thing that I'm going to count are these non-zero numbers, and I end up with four significant figures. So that's one type of measurement when we're dealing with zero. So leading zeros, never significant, never any exception to that rule. Um, the next type of zero are zeros when we get values like this. We'll say, so here's another type of zero, right? And these are what we're going to consider captive zeros. Captive zeros are always significant. Captive zeros are always significant. These are zeros that are in between two non-zero numbers, right? Zeros that are between, and let me write that down. So zeros in between two non-zero numbers, right? Zeros that are in between two non-zero numbers. So because these are captive, because they're in between these non-zero numbers, they're always significant, right? Always significant. So we do have to count them when we're considering significant figures here. So we have to count all of them. 1, 2, 3, 4, 5, 6. 6 significant figures, right? There's a captive zero here. And now I need to count all of them. This is 3 significant figures. Um, Captive zero. And actually, let's do this, right? I happen to have 1, 2, 3. They're all captive zeros. So I'm going to count all of them, and we have 1, 2, 3, 4, 5, 6, 7, 8 significant figures. So this is how we determine. So there's two types of zeros that we've seen now. So we've seen leading zeros as zeros that are out front, captive zeros as zeros that are in between values, and then we have then we have what we're going to consider trailing zeros, right? So trailing zeros are going to look like this. So we have 2, 5, 9, 0, 0, and then I'm going to write 2, 5, 9, 0, 0. But then I'm going to put this decimal point. I'm going to put it in another color, decimal point here, right? So these types of zeros here, these are what we call trailing zeros. Trailing zeros are sometimes significant. Some of the times are significant, and some of the times they're not significant. All right, but I have I, I mean, I've been teaching chemistry probably for about 6 years now, 6, 7 years now. I've been teaching chemistry, and I've come up with my very own formula in order to determine when these zeros are significant. Right. I haven't published any papers on it yet, but I don't think I've come across any case where this formula does not work, and so it's working really well. Um, so I'm going to give you guys this formula, so make sure you guys write it down. But there is a formula to determine when we count those zeros that are trailing and when we don't. So the formula goes like this. There. All right. So that is the formula you guys are going to use. It's huge. I know it's huge. Um, this is the formula you guys are going to use to determine when we consider trailing zero significant or not. If you physically see this, If you physically see it, not I know that you're looking here and you know that there's a decimal, right? I know that you know that there's a decimal there. There's an imaginary one, but I don't physically see it. But I know that you guys understand that it's there. I get it, right? If you physically see that decimal place, physically see it, count the trailing 0. If you physically see that in the number, you count the trailing 0, right? And this is only for trailing zeros. We've already talked about leading zeros. Decimal place or no decimal place, we never count a leading 0. Ever. Ever. Decimal or no decimal. Leading zeros, never count them. But trailing zeros, if you see that decimal place, count the 0, right? So here, I know that there's an imaginary one there, but I don't physically see it. So if I don't see the decimal, right? If you don't physically see the decimal, don't count the 0, right? So in 25,900 here, I don't see the decimal. This is 3 significant figures. Well, the bottom value, I see the decimal there. Now I need to count the trailing zeros. 5 significant figures. There's the formula, and it works every single time. It doesn't matter what the value, what the number is. 20. Do I see the decimal? Nope, I sure don't. That is 1 significant figure. 20. Now I see the decimal. Okay, well, now I have 2 significant figures. Again, so now we can, how about something like this? So 0, 0, 0, 2. How many significant figures? Well, I see that there's a decimal here, but I don't see any trailing zeros. Leading zeros, we've already discussed them. Well, they don't count. 1 significant figure. 0.00200. Oh, well, now I have some trailing zeros. I see the decimal point. I physically see it. I have to count the trailing zeros. 3 significant figures. Right? Okay, well, I know I don't have to count these because they're leading zeros. Here I have some captive zeros, so I should count those. And because I see the decimal, I have 2 trailing zeros that I also have to count. So we're going to go 1, 2, 3, 4, 5, 6, 7 significant figures. But in a value like this, 2010300, well, I don't see the decimal here. I know that there's an imaginary one there, but I don't see it. So the only values I'm going to count are these. My captive zeros looks like 5 significant figures. Right. So for trailing zeros, just remember that rule, and it should get you through determining all these values. Now, I know that you guys know how to round numbers, right? I know that you guys understand how to round. You were taught how to round in math, and we're going to kind of in chemistry we round it. We don't round differently, but we do ask you to do it a different way, right? The way we ask you is different, but the rules for rounding are the same, right? The rules for rounding are the same. If I ask somebody here, Can somebody round this number for me?
Yes.
What's the number? What? 20.
20.
Right? Perfect. So we're going to round this to 20, right? And why do we do that? Because the 1 is less than 5 when we round it down. If I ask somebody to round this number for me, well, can somebody round it? What do we round it to?
30.
Perfect, 30. So that's rounded to 30. Why? Because it's higher than 5 or higher, and we round up, right? So we're not changing those rules, right? But we are going to ask it differently, right? Let's look what we just did here. How many significant figures are in this value?
2.
2. How many significant digits are in this value?
1.
1. So we took a number that had 2 significant figures and rounded it to one that had 1 significant figure. And again, 2 significant figures, we round it to something that has 1 significant figure. So if I have this value here, 7,128, can somebody round this, remembering these rules up here that we just did, can somebody round this to 3 significant figures?
It'll be 7,130.
7,130. Is now I've rounded it to 3 significant figures. What it wouldn't be, and what some students try and do, they go, well, I need 3 sig figs. I'm going to round it to 713, right? But we can't do that because 7,128 is not rounded down to 713. Right? So please be cautious when we're doing that. Is that, yeah, absolutely, 7,130. What if I wanted you to round it to 2 significant figures? Then what would we put?
7,100.
7,100. What if I only wanted 1 significant figure?
7,000.
7,000, right? uh, so when we're doing this, what we're doing is we're adding insignificant zeros. Right? All of these are insignificant zeros, and we can get away with that. So if I have a measurement that says, if I want to put this in 3 significant figures, well, what do I have to do?
Add a 0.
Add a 0. I simply just add a 0, and now I have 3 significant figures because I added a significant 0. Right? So now knowing all of these rules for rounding and our significant figures is now we have to take these values and we have to maintain the correct number of significant figures when we're doing calculations. So let me write that down. I was wording it kind of new. So calculations and significant figures. So the first one we're going to deal with is we're going to deal with division and multiplication. Right? Addition, subtraction, we'll get to it, but it's easier when we're dealing with just multiplication and division. For multiplication and division, the significant figures come from, or you know what, let me say are determined. Significant figures are determined by the measurement with the least amount of significant figures. The measurement with the least amount of significant figures. So if we take, yes.
Oh, sorry, I have a question.
Uh-huh.
It's for the trailing zeros. If it's, for example, if it was like 10.0, would the zero after the decimal count? So it's,
Do you see the decimal place?
yeah.
And what is the rule?
So like all the zeros. So it'd be like, would it be three sig figs?
Correct.
Oh, okay. Thank you.
As long as you see that decimal point.
Okay. Thank you.
Uh-huh, no problem. Good question. So if I put a calculation up, let's put 2.334 centimeters multiplied by 0.320 centimeters, right? When I calculate this on the calculator, let's see what we get. We get 2.334 times 0.320, and I get an answer of 0.74688. All right, so this is our calculated answer from the calculator, but this answer is incorrect because it doesn't have the right number of significant digits, right? Is that the rule here is significant figures are determined by the measurement with the least amount of significant figures. Here we have 4 significant figures. Here we have 3 significant figures. My answer has to reflect the smallest amount of significant figures, 3, which means I now have to round this to 3 significant figures, and my answer is 0.747 centimeters squared. Right, the value with the least amount of significant figures. And it's the same thing for multiplication. In multiplication, or I'm sorry, division. Let's do 55 point, let's say 8752 divided by 50, 56.535. I think that's a good value. All right, so let's calculate this out. 55.8752 divided by 56.535, and this equals 0.98832. Well, let's take a look. I have 1, 2, 3, 4. So this is 6, and let me put it up top here. 6 significant figures. 1, 2, this is 5 significant figures. Is my answer has to reflect 5 significant figures. 1, 2, 3, 4, 5. So I need to drop that 9, and we're going to round this to 0.98833. 5 significant figures. And if we're doing multiplication and division, it's still all the same. Is that we can go, 3.6 times 2.8 divided by 1.2 times 0.6. And actually, let's do 33 here. All right, so here I have some values here. I have multiplication and I have division. So let's calculate this, and I got 33.6 times 2.8 divided by 1.2 divided by 0.6. And my answer is 130.667. All right, and you know what? Let me put some units in. Well, no, it's fine. I won't put units in there. 130.667. Here, this is 3 significant figures, 2 significant figures, 2 significant figures, 1 significant figure. Well, now what I have to do is I have to round this value to simply 1 significant figure, and it's 100. All right, so again, if we can combine these, right? So multiplication and division, and we have 1 significant figure as the smallest, reflected here, 1 significant figure. So this is how we maintain those significant figures when we're calculating out measurements. For for addition and subtraction is different. Addition and subtraction is different, and we have different rules for that. And we can't mix up those rules, right? So now we're doing addition and subtraction. So addition and subtraction. Um, for significant figures, so excuse me, to determine significant figures, we use, sorry about that. To determine the significant figures, we use the measurement with the least amount of decimal places. The measurement with the least amount of decimal places. So let's put up a couple problems here. So we'll say 486 subtract 421.23. And for those of you, I have OCD a little bit, and I get it, and you're like, I know what they teach you in elementary school, and oh, we have to line up the zeros, and you arbitrarily put these 2 zeros in here. No, 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 no. We can't do that. It might look a little funny, but I know that you know there's an imaginary 0 there, and we can still subtract this without having to physically see the zeros, right? So don't put in significant digits or insignificant digits, right? We need to make this calculation. So our calculation ends up being, what is this, 6, 7, 7, 4, so 64.77. So we have to go with the least amount of decimal places. Here, this is 0 past the decimal. And here, this is 2 past the decimal. Well, that means I have to go with the least amount of decimal places. So I need to round this number to 65, right? And I end up with 2 significant figures. So it is okay that they don't match, right? Because here I have, what is this? I have 3 significant figures, I have 5 significant figures, and my answer has 2 significant figures. And that's perfectly okay because I followed the rule of the least amount of decimal places. So if they happen to match the smallest amount, it's simply just coincidence. But what you're looking for here is you're looking for the smallest, the least amount of decimal places. But we go with, let's do one that's addition here. 92 plus 0.9 All right, let's go ahead and add this. I got 1, 11. This is going to be 10. Well, what do we see here? This is 1 past the decimal. This is 2 past the decimal. Is that I'm going to go with 1 past the decimal, and my answer is now 10.1, right? I have one that's 2 sig figs, the other one's 2 sig figs, my answer is 3 sig figs. That's perfectly fine because I followed the rule for addition and subtraction. I went with the least amount of decimal places, and I have 10.1 as my answer. um, and sometimes we have what we call mixed order of operations. Sometimes we have to do multiplication, division, and subtraction. So if we're doing all multiplication, because you don't really want to do sig figs in the middle of your calculation, right? But if you have a calculation similar to this, where it's all multiplication, it is all division, it's all multiplication and division, don't do your significant figures until you're at the end, right? That's when you determine your significant figures. Don't do it in the middle. But when we have mixed order of operations, that's a little different because we do have to keep those separated. So let's actually do one where we're going to calculate density. So we're going to calculate density um, with mixed order. With mixed order of operations. Let me see here. Oh, come on. So when we're calculating density of odd shapes, could be rocks, could be some odd shaped metal, um, a piece of gold, piece of silver, whatever it is that we're uh, trying to get the volume of, is that we can use displacement, right? If I measure an amount of water, I have some initial volume, and we can see the initial volume here. So the initial volume is 13.5 milliliters. And when we put the piece of rebar in there, well, the water displaces and it does move up. And the difference in those two values between the final and the initial is the volume of the object that is in there, right? And when we do that, it is always when we're taking, and I'm going to use this delta symbol. This delta is just kind of shorthand for change. It does mean other things. It can mean, heat. It can represent, but sometimes we just use it as just meaning change. So to get the change in volume, this is going to be, it is always going to be final volume minus initial volume. If we're doing temperature change, it's final temperature minus the initial temperature. If we run into a negative temperature change, that's fine. Don't be afraid of negative numbers, right? Volumes, we're never going to have negative volume, but sometimes when we're calculating energy, heat, we're calculating temperature, sometimes we have a negative value there, so that's fine. But just always remember the rule of thumb that it's always final minus initial, final minus initial. So if I were to give you a couple of values, um, and we wanted to figure out the density. So the density, let's see, if we're looking at, if we wanted to know the density of that rebar there, right? Well, let me get these values. So it is 69.658. So our mass is 69.658. And then we're going to have two volumes here. So we have final volume and we have initial volume. Initial 22.4, 13.5. Milliliters. Well, when we set this up, right, so to figure out our density is equal to our mass over volume, right? So in order to figure out our density, we're going to have 69.658 grams over 22.4 milliliters minus 13.5 milliliters. Well, this is mixed order of operations, right? So the first thing we need to solve here is we're not going to just solve it. There is one way. Yeah, I can put this all in a calculator in one shot and get an answer. But that answer might not be correct because my significant figures are going to be off. If I can't solve this unless I do the subtraction first, and I have a different rule for subtraction, right? So 22.4 minus 13.5, I get 8.9. I use the rule for subtraction, one past the decimal, one past the decimal. My answer is one past the decimal. So now in order to calculate density, density is equal to 69.658 divided by, oh, this is grams, divided by 8.9 milliliters. Well, now I'm doing division. 69.658 divided by 8.9, and I get an answer that says 7.82674 grams per milliliter. Well, let's take a look at it. 5 significant figures, 2 significant figures. My answer is 7.8 grams per milliliter, because I'm following this mixed order of operations here, right? I have to do the subtraction, right? This is not PEMDAS here. Like first we figure out the subtraction. That's what's in the parentheses. I can't figure that out until, right? I can't calculate density until I've figured out what that subtraction is, right? Then I can do the division here. So we have 7.8 grams per milliliter for that one. So that's just kind of an example. Like we already kind of went over how to calculate density or whatnot, but this is just kind of an example to show you if we have to do mixed order, how we would go about solving that. So now going on to some terms, right? We have a couple terms, more terms to learn. Accuracy and That's not, I'm not an English major. There we go. Accuracy and precision, right? So accuracy and precision, we can think in terms of just kind of a bullseye here. We have 3 targets. I know they're not perfect circles, but let's do the best we can here. Is that if we were to take a shot at these bullseyes, right? We hit it 5 times right there, dead center, right? This is what we would consider accurate and precise. Accurate and precise. If we take the same shot at another bullseye, but let's say we're out here, all my shots are still lumped together. Why does the book say centimeters versus milliliters? Because they mean the same thing. When we're talking about uh, another way that I could write this answer is 7.8 grams per centimeter cubed, is that 1 milliliter is equal to 1 centimeter cubed. Does that help, Michaela?
Yes, thank you so much.
Okay, no problem. So here, if they're all lumped together, but I didn't hit dead center, right? Well, this is what we would consider simply just precise, and not accurate. You know, if I'm spreading buckshot everywhere and not even close, right? This would be neither precise or accurate. Right. And this is how we can think of accuracy and precision. So that if I were to actually give you some values now, right? Let's actually look at some values. For something that's accurate and precise, let's say that our theoretical goal was to measure something that was 283.0 milliliters. Right, and I go and I start measuring out, and I get 4 attempts to measure this value out with my graduated cylinder, right? So, well, I'm going to put theoretical. So my theoretical value here is going to be 283.0 milliliters. And I take some measurements, and I got 283.1, 283.2, 283 point. Oh, we'll go 282.9, 282.8. I would consider this pretty accurate, pretty precise. That I'm very close to 283.0, right? Well, as far as precise but not accurate, we could think of these in terms of measurements. Let's say we're at 292.1, 292.2, 291.9, 291.8, right? Uh, I'm precise. My measurements are really close together, but I'm just not accurate. I'm not at the 283.0 milliliters, right? So looking at these actual data here, and then something that's not accurate or precise. I mean, if I'm using some instrument and I'm at 298.6 and I'm 275.3, 281.6, 301.5. I'm not accurate or precise, right? So we can see from just a list of measurements whether we're accurate and precise but maybe not accurate, or we're just not even in the same ballpark as accurate or precise. So those are just some terms to go over. So now that we kind of understand significant figures and zeros, trailing zeros, we can start getting into what we consider dimensional analysis. So dimensional analysis is how we convert units, right? Uh, how we can go from centimeters to inches, from miles to feet, from kilograms to ounces, and I'm sorry, kilograms to pounds. But what we use for dimensional analysis is we use what we're going to call a unit conversion factor. And a unit conversion factor is simply just a ratio of two equivalent quantities, with different measurement units. And this is what we consider a conversion factor. So a conversion factor, a ratio of two equivalent units. So we can say 2.54 centimeters is equal to 1 inch, right? Two equivalent units with different, or two equivalent quantities with different measurement units. That these are equivalent quantities, 1 inch, 2.54 centimeters, with different measurement units. So when we use, and this is what we actually consider, this is what we're going to consider a definition. Our conversion factor is the ratio of this, right? So if I were to put this into a ratio, I can write it as 2.54 centimeters over 1 inch. Or I can write it as 1 inch over 2.54 centimeters. And these are conversion factors, right? Those are conversion factors. 60 seconds is equal to 1 minute. So there's my definition. And if I want two conversion factors, I can go 60 seconds over 1 minute, or I can write it as 1 minute over 60 seconds. Right. One more here. We can go 1 pound is equal to 454 grams. And if I need a conversion factor for this, 1 pound over 454 grams, or I can write it as 454 grams over 1 pound. My conversion factors. And we use this again to convert from one type of unit into another type of unit. That if I have 23.6 pounds and I want to convert to grams. If I want to convert this to grams, well, I'm going to need one of these two conversion factors, right? For the next, for the rest of the semester until June, our entire goal here is to simply just cross cancel out units. cross cancel them out. We're chemists. There's a lot of stuff we can do as chemists. And one of the things we can do is we use reciprocal values. However we need to flip it. However I need to flip something in order to get my units right, well, we're allowed to do that. So if I start out with 23.6 pounds, I need to set this up so that I could cross cancel. And the only way I can do cross cancel is I can cross cancel something in the numerator to something in the denominator, which means that I'm going to specifically need this. Both of these conversion factors will not work in order to cancel this out. If I use the wrong one, this is what happens. 1 pound over 454 grams. Well, does this cancel out this? Well, it sure doesn't. I'm going to get pounds squared. Pounds times pounds, pounds squared. And that's not what we're looking for, right? We're looking to simply cancel out these units. So if I were to write 454 grams over 1 pound, then we can see that these easily cancel out. And I get 17.5383. And now we're looking like, okay, well, now let's take a look at significant figures. Well, my measurement is 4. Nope, this is 3. I thought that was a 1 there. This is 3 significant figures. And I want you to see something here. Conversion factors. Conversion factors. Let me tell you something about conversion factors that you might want to remember. Is that we do not use conversion factors to determine significant figures. Conversion factors are what we consider exact numbers. Exact numbers like, if I count no, I have 2 cups on my desk. I have 5 pennies on in the drawer. I have 25 participants in Zoom. I have 1 keyboard on my desk. I have 2 calculators on my desk. Like stuff I can count. Those are exact numbers, and definitions also are what we consider exact numbers. When we write the term 2.54 centimeters equals 1 inch, that's exact. 2.54 centimeters is exactly 1 inch. 2.53 centimeters? No, that's not an inch. 2.55 centimeters? No, that's more than an inch, right? There is exactly 1,000 milliliters in 1 liter, right? There's not about 1,000. No, uh, exactly 1,000. Exactly 1,000 milliliters is a liter, right? So we don't use conversion factors in order to determine significant figures. So the 454 grams over 1 pound is a conversion factor, and I'm not going to consider either one of those, or else my answer would just my answer would simply just be, what is it, 20? And I'm not going to round it to 20, right? So we need 3 significant figures from our measurement, and our answer becomes 17.5 grams. 3 significant figures, 3 significant figures. Is that we don't count conversion factors definitions towards our significant figures. Uh, sometimes we're going to require more than one conversion factor, right? If I want to convert, let's go 2.5 feet cubed into centimeters cubed. Right. Well, we're going to need a couple definitions for this. One definition we can use is that 1 foot is equal to 12 inches. And we know that 1 inch is equal to 2.54 centimeters. Well, we have 2.5 feet cubed. Well, the first thing we're going to want to do is we need to get rid of those feet cubed. And if I put feet down here, I can put, what is it? 1 foot is equal to 12 inches. But it's feet cubed. I can't get rid of feet cubed with simply just one of these. So there's a couple of ways to solve this. I could do this and I could say, okay, well, let me multiply it by another 12 inch over 1 foot. Well, that would cancel out 2 of them. And then if I do it again by 12 inches over 1 foot, well, that would get rid of all of them. So these units would all cancel out. So there is another way to do that, and the other way to do that would be 2.5 feet cubed multiplied by 12 inches over 1 foot and cube that, right? So I take the conversion factor and I cube the conversion factor, then it would simply do what I need. And then we could also use the next one. And because I'm in inches cubed, and we're trying to get to centimeters cubed, is that we would use, what is this, 1 inch over 2.54 centimeters, but we're looking for centimeters cubed here, which means that I also have to cube that as well, and I would have some answer. And we can just go the long way. It doesn't really matter. Let's do both here. So right now we've canceled out feet. And now we need to convert inches into centimeters. So we'll go 1 inch by 4 centimeters. And again, the units simply still cancel out inch, 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 inch. And both of these answers are going to be the same here. So when we calculate this, 3.5, 12 cubed, 70,792.1 cubic centimeters. But let's see here. Conversion factor. I'm just going to use my original data of 2 significant figures. 70,000. Nope. That's not going to work. I'm going to have to put this in. Nope, that would cut 71,000. There we go. 71,000. 2 significant figures, centimeters cubed, or you could write it as 7.1 times 10 to the 4 centimeters cubed. Either way, they're both correct answers. I wouldn't mark either one of those wrong. And that leaves us just enough time to go over temperature. I don't spend a lot of time on temperature simply because they're formulas and you plug in the value and out comes some number, right? So for temperatures, we have Fahrenheit, and we have Celsius, and we have Kelvin. So in order to calculate Fahrenheit, we can calculate this from Celsius. So Fahrenheit is equal to, I use 1.8. The book might use 9 over 5, but it's exactly the same thing. 1.8 is equal to 5, 9 divided by 5. It's the same. So 1.8 multiplied by whatever your degree Celsius is, and then you add 32. In order to calculate Celsius from Fahrenheit, Celsius is equal to the degree Fahrenheit minus 32, and we can divide that by 1.8. And in order to figure out Kelvin, Kelvin is equal to degrees Celsius plus 273.15. And there's no degree Kelvin. It's just simply just Kelvin. We have degrees Fahrenheit, degrees Celsius, and then Kelvin. We don't have degree Kelvin, right? But all of these here are definitions, right? They're all definitions. And what did we say about definitions and significant figures? Right? Definitions do not use any conversion factors to determine significant figures, and that is to also include our definitions, right? So let's see if we can calculate something here. So let's calculate 80.92 degrees Celsius. Let's convert that to Kelvin. And let's convert it to degrees Fahrenheit. All right, so as far as Kelvin goes, Kelvin is equal to degrees Celsius plus 273.15, so we have 80.92 plus 273.15. All right. So here, let's go ahead and do that math, and we have 273.15 plus 80.92, and we get 354.07 Kelvin. And what I'm looking for here is, well, I have 2 past the decimal. My answer is 2 past the decimal. All right, so now let's figure out Fahrenheit. Right? Fahrenheit is 1.8 times a degree Celsius plus 32. So in order to figure out Fahrenheit, 1.8 times the degree Celsius, which is 80.92 plus 32. All right. So let's figure that out now. 1.8 times 80.92 and I get 177.656. But here, four significant figures, 177.7 degrees, Fahrenheit. And I guess one thing we should note from all these degrees is that there's 3 different temperature scales here, 3 different temperature scales. When water, where these kind of were developed. So Celsius was developed around pure water, right? Is that water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. And this is where the Celsius scale comes into place. Now, as far as Fahrenheit goes, water boils at 212 degrees Fahrenheit and freezes at 32 degrees Fahrenheit. And there's about a 180 degree difference there. There's a 180 degree difference there, but Fahrenheit where this came from is when water freezes. When it's 0 degrees outside, that's when brine freezes. Seawater freezes at 0 degrees Fahrenheit. So pure water, they found out, didn't freeze at 32 degrees Fahrenheit. I'm sorry, at 0 degrees Fahrenheit. That it froze at 32 degrees Fahrenheit. So Fahrenheit was developed around brine, and the Celsius was developed around pure water. And then we have the Kelvin scale. Kelvin scale. Oh, and one other thing, like Fahrenheit and Celsius can be negative. You get -5 degrees, -20 degrees, never got -100 degrees, but Kelvin cannot. Kelvin cannot go past 0 Kelvin. Like that's as cold as anything will get is 0 Kelvin. Perfect crystals form here, um, but 0 Kelvin. So you're never going to have a negative Kelvin. Okay, it's simply just going to be 0 Kelvin, and it is finite, and that's where the Kelvin scale ends there. And I think we have just completed Unit 1 here.